Welcome to this video of the tutorial on MCTDH-X. It is based on this manuscript on the archive, MCTDH-X, the multi-configurational time-dependent Hartree method for indistinguishable particle software. In the last video, I have shown how to use the provided bash script to do a complete procedure of MCTDH-X in order to reproduce the figure 2 and also figure 3 of the manuscript. In this video, I will go through the simulation results and show you how to interpret these results. As an example, we will go into the folder relax1 fig2 abc. And now we can see that the program has generated many files. An important one is the nopr.out files. In order to know what data this output file provides, we can refer to the manual under this link. So this is the web page, and in the web page we can further click on this link, output structure in standard MCTDH-X computations. And the first table is the NOPR for the nopr.out files. So each row in this file corresponds to one time. And in each row, the first column or the first entry is the time or the imaginary time in a relaxation. And then from the second column on to the second to last column are the orbital occupations. We should note that the first orbital, which has the highest occupation, is placed at the second to last column, and the last orbital, which has the least occupation, is put at the second entry. And finally, in the last entry, it is the energy at that particular moment. Now let's go back to our simulations and look at the last 3 lines of the NOPR files. So first we note that these are the time 9.9, 9.95, and 10. And at these 3 time units, we look at the energy and find that the convergence is really good. It converged already to the 12th digit after the decimal. And in this case, we would say that the convergence is already enough to claim that our simulation has converged. So furthermore, I would like to show you how this energy evolved as a function of the imaginary time. We could see that indeed it drops very rapidly in the beginning and then more or less converges in the end. And so are the orbital occupations. For example, we are plotting the occupation of the first, second, third, and fourth orbitals. We can see that the occupations also change very rapidly at the beginning and then converge starting from time unit equals to 2. And we can see that in this case, only the first 2 orbitals are macroscopically occupied. And then from the third orbital on, it is more or less irrelevant. So other than the nopr.dat files, we further look at the orbs.dat files and the coif.dat files. To explain these 2 files, we first look at the manuscript and look at the ansatz of the MCTDH-X at equation 4. So as shown in equation 4, we know that a many-body state in MCTDH-X is determined by 2 things. One is the orbitals. This is the orbitals. And the second one is the coefficients. This one. So with the coefficients, and orbitals, and both of them are time dependent. And by determining these two things, we are able to determine the many-body wave function. So in our simulation results, these files are the files which store the orbitals, and these files are the files which store the coefficients. The coef.dat files store the coefficients. And furthermore, we should note that these dat files are only for the humans. So these ASCII files are only for the humans, and for the computers, it uses these binary files, CIC bin, headers, and psi bin files to read and store the coefficients and orbitals of the many-body wave functions. And so to look at the output of these ASCII files, orbs.dat and coef.dat files, we can also look at this manual. And we find that in the table 14 here, this is the structure of the orbs.dat files. And we can see that the first column is x, the position, and the fifth column is the current one-body potential V, and the sixth column is the current density distributions. So these are what we usually interested in. So for example, since our simulations has converged at time unit 10, we look at the result at time unit 10. So first of all, we plot the first V versus the fifth column. So this is the double well potential that we are simulating our many-body systems in. And then we are looking at the density distribution. So this is the density distribution. So we have clearly a double peak distribution. So this is the orbs.dat files. And the next files we are interested are the results of the analysis. This includes, for example, the k-density.dat files, which shows us the density distribution in the momentum space, and these x-density files are the results in the real space, and also the correlations in the real space, and the single-shot images, x-single-shots.dat and x-single-shot-average.dat files. First of all, let's look at the k-density and x-density files. So the structure of these files are shown in, so this is the main page of the manual, and the structures of the analysis output files are shown in this here, structure of the output file of the analysis program. So the first table shows the structure of the x-density files and the k-density files. So the first column are the x or kx, the position or the momentum, and then the fourth column is the density distribution in the real or momentum space. So for example, but there is one caveat, which is that in x-density files and k-density files, the result is shown as n times the density distribution, where n is the number of particles. So in order to compare the x-density files and the orbs.dat files, we need to divide the result in x-density files by the number of particles. So this is the x-density files. So we are plotting the first, which is the position versus the fourth column. but now we want to divide it by the number of particles, which is 6. And then we want to compare it to the orbs.dat files, but with the 6th column, because in the orbs.dat file, density distribution is stored in the 6th column. So we can see that they are exactly the same, which it should be in the two files. And furthermore, we can also look at the k-density distribution k-density file to look at the density distribution in the momentum space, and we also want to divide it by 6, which is the number of bosons. So we can see here that it is clearly density distribution in momentum space showing 3 peaks, and these two peaks lower peaks, they show that there is superfluidity between the two wells of the double well potential. And last of all, and the next one is the X correlations files. So the structure of the X correlation file can be found here. So this is the x correlations.dat files. So the correlations is always between 2 points, x and x prime, and we can see that the position x can be found at column 1, and the position x prime can be found in column 4. And then at the column 7, and now we have I equals to 1. So in column 7 and also column 10, we have the density distributions at position x and also in the position x prime. And then at column 8 and 9, it is the real and imaginary part of the reduced one-body matrix. It is the real and imaginary part of the reduced one-body density matrix. And at column 11, it is the real part of the reduced two-body density matrix, which is a real number. So now we have the structure of the x correlations.dat files. So now we want to also plot it, but now instead of plotting the reduced one-body and two-body density matrices, we rather want to plot the one-body and two-body correlation functions. So in order to do that, now we want to plot the x correlations.dat files, and then we use the first column for x, fourth column for x prime, and then the definition of the relation between the correlation function and the correlation function and the reduced density matrix can be found in equations 7 and 8. So this is the reduced density matrix, and this is the correlation function. So we can see that it is given by, for example, the one-body correlation function. It is given by so this is the real part and imaginary part of the reduced density matrix, and divided by the square root of the product of the densities. So this is the reduced. So this is the one-body correlation functions. We can see that in the diagonal terms, the correlations is unity equals to 1, and in the off diagonals, the correlation is slightly smaller than 1, showing that there is superfluidity, but it is not 0. It is really far from 0 and far from 1, so showing that there is superfluidity between these two wells. And of course, we can also try to plot the two-body correlation functions. It is defined as the column 11, which is the reduced two-body density matrix, and divided by a product of 7th and 10th column. So this is the two-body correlation function, and we can see that the off-diagonal term now is almost unity, while the diagonal term is slightly less than 1, but also far from 0. Finally, let's look at the single-shot images in the single-shots.dat file. So in this table, we can see that the first column is the position, while from the 4th column on, each column is one single-shot image. So, for example, let's randomly take one image, because we have 10,000 images, so we take the column 443, and this is one image. So we can see that there are four bosons on the in the left well x smaller than 0, and there are two bosons in the right well x larger than 0. And let's randomly take, for example, 2312, and in this image there are also three bosons, 1, 2, 3, three bosons in the left well, and 1, 2, 3, three bosons in the right well. And so the single-shot images is taken according to the wave function. So which means that here, in each single-shot image, the positions of the particles are drawn according to the wave function, or squared. So, for example, if the particles are completely uncorrelated, so let's show the density distributions. So if the particles are completely uncorrelated, then the distribution of each particles would be completely independent from each other. So whether if the first one is here, maybe then the second one could still be anywhere but taken according to these density distributions. However, they are independent from each other, and this is the superfluid limit. If we count the number of atoms in one well, for example in the left well, then this would follow the binomial distribution. On the contrary, if the system is already in the Mott insulator phase, then there would be a very strong correlation between the particles. And there would be exactly, when there are in total 6 bosons, there would be exactly 3 bosons in the left well and 3 bosons in the right well. So we can use the single-shot images to look at the correlations between the two wells. So this is already shown in figure 3. The blue bars are showing the results from a extremely superfluid case. So you can see that the distribution is binomial, and the orange bar shows a case which is not so superfluid. So you can see that the contribution from of 2 n equals to 2 and n equals to 4 is still significant. However, the green bar is already in the most insulating phase. So there were exactly 3 bosons in one well. And however, if we are using fermions instead of the bosons, then because of the Pauli principle, the fermions would already tend to distribute it as three fermions in each well, regardless of the strength of the interaction. So in this video, we have seen how to interpret the results from the analysis. In the next video, from the next video on, I will show you how to use the more complicated bash script to do the simulations partially manually.